Okay. Hello? Yes. Okay. Good morning. Can you hear me at the back? Okay. We have a few things before the lecture. Okay. One thing is about registration. Okay. We got a very long waiting list. Besides, we got solid booked with 200 students. We have another 90 on the waiting list. Okay. I have been discussing with the department. Maybe we can find a solution, but until now, I cannot announce we already got a solution because we still have something to work out. Okay. So for people on the waiting list, you are still encouraged to attend the lecture. Likely, maybe today, maybe Thursday, we may be able to find a solution to get a good number of them from the waiting list. But one thing I probably should say is definitely we cannot get all of them. Okay. But whether we finally can work out even get one of them to get into the regular class, I cannot guarantee. But I can guarantee not everyone can get in. Okay. So that's our current situation because the department has overall arrangement. I try to work it out. Okay. So be patient. We definitely will resolve it before the end of the second week, which is before the end of this week. Okay. So that means a yes or no will be determined likely by Thursday, okay, as the latest. Then about the regular class. Okay. First thing is the homework is ready, is released on the web. What you need to do is you go to the lecture page. There's a link to assignment 1. You click it, you will be able to find the assignment. I think the assignment is due September maybe 15th, around that time. That means you have to start working on it now before it's too late. Okay. Some, because the data sum is a little big, you need to write a small program instead of you calculate by hand. If you get thousands of data items, I don't think you have time to calculate by hand. Okay. So you may need to write a tiny program. You don't have to hand in the program, but you have to run it to get the results you can put in. Okay. So I strongly suggest you to look at today. You start it early. Okay. Before the last minute, you got a panic. You cannot finish on time. Yes. I think it's already posted. Last night, I actually sent an email to TA to ask her to post it. If it's not posted, it will be posted early this afternoon. Okay. I will check with her again. They should be there. Okay. So that's the first thing about the first homework. Okay. The second thing is about fourth credit. Okay. I actually do not encourage the student to take the fourth project because the class is really large. Okay. TA needs a lot of effort to work with you. If we get hundreds of people, maybe we run short of hands. But we do have specified what is a project for the fourth credit. Okay. If you feel the workload is too heavy, you can send me email, change fourth credit to 3 credit. Okay. That means the fourth credit definitely is not free. It's a lot of work. Okay. If you want to work on it, fine, you stay there. But if you don't want to work on it, don't want to invest a lot of time, you change it. You are afraid to change at the early stage. Okay. So the fourth credit essentially is there's a conference called Wisdom, Web Search and Data Mining, Wisdom Conference. They have Wisdom 2017, Wisdom Cup. Cup means like a programming contest. Okay. It could be a lot of fun, but if you don't have time, you have to think about it. Okay. What is this cup is doing? They have 2 tasks. one called triple scoring, one called vandalism detection. Okay. I'm going to give you in the next page say what they are. Okay. Then you see whether which project you want to join. If you take the fourth credit, or you just don't want to join, just want to quit, then you change. Okay. The submission actually is you team up. Not necessarily everyone will do this project. The first thing is you only choose one. Another thing is you need to team up with several students who take CS for 12, the fourth credit, form a small team, then you work together as a team instead of you work alone. Okay. You work alone may be too heavy for you. Okay. And then the grade will be based on, because they have lots of testing, lots of milestones, different testing. And where you are is clear. You cannot hide. You can be ranked. Suppose there are 300 teams are working in competition. If you rank number 300 as the last one, then look unlikely, you did something interesting. Okay. But if you rank top 10, definitely you're one of the heroes, right? So they constantly have the scoreboard. We can watch, you can watch as well. Okay. And the registration and information, we want to get the team stable before we have a meeting. The stable means you read it, you say, I don't want to do it, you drop it, okay, then we will not have a meeting with you. So we only want to meet with a group that really want to do it. Okay. So now I give you a little detail on the first one is triple scoring. What is triple scoring? That means you get a very large corpus. Okay. It could be on the web, it could be somewhere in the documents. We do not know, but they are going to give us a lot of text documents. Then they are going to have you automatically generate a lot of triples. And they want to see those triples are true. That means you judge. They give you a triple, say whether this one is right or wrong. You may automatically judge whether this one is right or wrong. For example, they may say, Johnny Depp, profession, actor. If Johnny Depp in the real world is really actor, your score should be high. But if you got another one, you said Quentin Tarantino, the profession is actor, likely you should give a low score because he is more a director rather than actor. Okay. For example, the same thing as you say Barack Obama. Okay. If you say Barack Obama is a president, likely you will get a high score. But if you say he is a father or an author, probably that's not his major goal. The score should be somewhat lower. Okay. So you probably know you need some intelligence built up in your system. Okay. You will be able to identify what is a major role. This triple is right or wrong, is a majorly should be promoted or should be demoted. This should be done automatically. Of course, it's not that easy. But the TA and I will give you some hints or give you some techniques you may try. This is data mining, essentially, right? You got lots of data, you try to mine it. And you do have training data. That means they give you some corpus. They give you something is right. Okay. You get a training data, but you need to finally work out. They give you the new triples. It's not in the training data. You should score it right. The score is between 0 and 1. If it's true, it should be closer to 1. If it's false, it should be closer to 0. Okay. So that's the very interesting project, but it's also a challenging one. Okay. The second one is vandalism detection for wiki pages. Wiki page, anybody can edit it. What about you put an ad, you put a rumor, you put something wrong inside? Okay. So because wiki has almost millions of pages. I do not know exactly, but it's a very huge number. You cannot hire a human to check every edit, especially the edit could be vandalism. Okay, it's very hard to find. And they want to develop a software which can automatically detect vandalism. That means if this guy is really trying to ruin this page, or put rumors, put some wrong things in this page, you will capture this page automatically. Okay. Can we do this? Okay. And actually, I do have one PhD student. He's doing his profession, or his major claim is doing something not far away from this. Okay. And he actually is volunteering to supervise the group. That means if you are interested in working on this, likely he will give you a lot of instruction. Okay. So, but they do have training, they have the testing, the whole thing actually is under his supervision. Okay. The number one project is more under our two TA supervision because they are very familiar with the chippers. Okay. So, if you are interested in joining this as your fourth credit, okay, you stay. Okay. Of course, if some people only register 3 credits, you said, I would really, really devote on this. I would change to 4th credit. I want to take 1 more credit, but I can work together with some PhDs, get a cup. Okay. Fine, you discuss with me, we may put you in. But on the other hand, if you feel, oh, that's too much work, originally I was thinking 4th credit is free. Now it's too much work. I have to drop the 4th credit. Fine. Okay, at this point, you will not get any penalty. You just drop it. But you have to officially sending me emails. I forward to the registration desk, okay, in the department. They are going to drop you. I have no authority to drop you. Okay. They are going to, once they get your email at this early stage, you're free, you can drop it. Okay? So that's the thing. Any questions related to this? It could be fine. If you really think you want to devote on it, it's fine. You can even change from 3 to 4. Okay. Yes? Is there any limit number of teams? Usually we want to have small number of teams we can check. We don't like every single person as a team because it could be too much work and you have nobody to discuss. Okay. But if you say 3 people, 5 people, up to 7 or 8 people form a team, that's also possible. But I don't want the whole class just one team. You cannot even distinguish each other, right? So that's the one you can just assume. For each task, we may have 3 or 4 teams. Any other questions? Okay. So you can talk to me after class if you are in the 4th credit, especially. But if you are in the 3 credit, you get highly motivated by watching this too. You also can discuss with me. Yes? For people in the waiting list, we have to say, at this point, at the waiting list, you probably don't have to consider this because the waiting list is too long. Okay, we may not be able to handle it, even getting you in. Whether getting you to the team is another issue. But if you are really interested, you really want to participate, you're free. Okay, you can participate even without registering the 4th credit. That's possible. Okay. Any other questions? Okay. Thank you. Now let's get into, we will continue our discussion on the visualization. Okay. Last time we discussed, we said visualization has lots of different ways. We show you some, for example, geometric one. You probably saw the scattered plot matrices. You got landscape. You got parallel coordinates. Those are geometric methods. Another method for visualization is icon-based method. Icon-based means we use different kinds of icons. For example, the typical one like stick figures and Chernoff faces use different faces even. But since they are in different shapes, they represent different things. Then they can put things in. You will recognize a lot of interesting things. Those we call icon-based visualization. Each icon represents certain information. Okay. For example, you get a shape. You can code shape means what, color means what, tire means what. You can get all the different things means different thing. Once you plot in the figure, it means something interesting. Okay. For example, a quite popular used one is Chernoff faces. Okay. Chernoff faces, you probably saw lots of those figures, some smiling, some angry, those are things. But this is a little more complicated. Okay. You probably can see Chernoff face is one kind of face developed used in Mathematica. Anybody knows Mathematica? You probably use it. Actually, Mathematica, quite a big team, development team, is in Champaign, UIC. And actually, the CEO is something closely tied with UIC. Visited the computer science department quite a few times. Even his home base is in Boston. And you probably can see that's the one typical Chernoff face figure. You probably see there. Here you got 16 figures. But you look at the eyes, may mean something. The eyebrow, the nose, and the mouth all mean something. Even the shape of the face may have different encoded meaning. Okay. Then they put those faces into the figure. They actually getting you a lot of real information out of it. So it's not only looks interesting, but it's also hidden or carry a lot of information. Okay. You think about it, you may get a multi-dimensional information hidden in your nose, mouth, and eyes. Right? This is another one called stick figures. I do not know. Sometimes I go to some professors, especially in statistics, those professor office. Sometimes the inside office, sometimes the outside office. They actually post some kind of figure like this. It's quite interesting. Actually, in different campuses, I saw quite a lot of professors in math and statistics who put those figures there. What does this mean? Okay. This actually is a good statistics figure. You can see this part, the x-axis means income. Okay. The income is high. You probably can the figure, those stick figure will be in the high end. Okay. Otherwise, in the low end. The other one is age. Okay. You probably can see here, even you do not know the figure, you probably can see some people are very young, get very high income, this part is very sparse. Simply says when you were very young, you probably will not make a lot of money. So this part is sparse. But you can see those old people, not too old, actually their income is much higher. You can see this part, right? That's just without looking, just look at the figure distribution. But actually figure carries a lot of other information. For example, some figure may tell you about the education or gender or some other things. So they use this different, like a small animal, those kind of figures, actually carry a lot of information about other pieces of information to put in. Then they put this figure there. People can read it. It will make a lot of sense. They will say, here I probably only make sense is the density of the figure. I say the very young people, the income is not very high. Okay. That's probably you can easily see it. But see other things, you have to look at this animal shape. Okay. Then you probably will see, a gender, education, all these things. So those are the visualization. It's also pretty nice and very popularly used. Okay. Then, besides those icons, there are very popular method for visualization is the hierarchical visualization. Hierarchical visualization means you put things in a 2D, 3D, like some kind of hierarchies. Something is, for example, tree shapes or cubes, so you can watch it. There are several popular methods. One called dimensional stacking. That means you cannot see high dimension things, but you can stack high dimension things in a low dimension space. Okay. For example, if you look at those those small figures, actually this is 2D. Okay. The small one is 2D. But you want to nest it in another 2D space, so you get a 4D, you can watch it. So this is called dimensional stacking. Okay. And this is words within words. This is the tree map. This is home trees. This is info cube. We are going to show you one by one. Okay. First is dimensional stacking. Dimensional stacking means usually people can easily see 2D things, but it's very hard to put a high dimension into a 2D space, because you look at your computer screen, it's 2D. How could you put high dimensions there? You can stack. For example, there are total 4 attributes, or you say 4 dimensions. For this 4 dimension, you can plot dimension 1, like attribute 1, attribute 2, as 2 major x, y axis, right? Then, for each small circle, actually that means for this particular value, attribute 1 and attribute 2, you got a small space. That space, you can get another small x and y to put attribute 3 and 4 value there. Then you can stack them together. So this is a way to stack the dimension 3, 4 inside this dimension 1 and 2. Okay. So you can get 4 dimensions easily. Just give you a simple example. This is the one you probably can see the distribution nicely, right? We already showed the scatter plot. You can get scatter plot matrices. Okay. This one is showing you get this one like a histogram or something like this. Then you can get the dimensions 3 and 4 stacked inside 1 and 2. You can easily see the distribution. Okay. For example, this part of the dimension 1 to this part is very empty. That simply says dimensions 3 and 4 almost shows no value. But the others could be quite dense. You can see. So this is a nice way to show 4D in the 2D space. Of course, you can even stack more Ds inside, but you just cannot see that clearly. This one is words within words. Okay. Each word you can think is a 3D space. You can see this is a 3D, like a curved, surface. But you want to put into another 3D dimension, right? You can see this is a 3D, but you get other 3D. You want to put it in, and how do you put it in? This is like a 3D stacking. Right? You get a 2D stacking. You can get 4 dimensions, and you get 3D. You can say this word actually stack inside of this part. Okay? So you get words within words. So that's there are some software companies, they actually produce those kind of words within words pictures. So for people visualization, if you want to see more Ds, their relationships, you actually can use these words within words. Another one is a tree map. Tree map means you want to organize things into trees, but the trees looks very scattered and take a lot of space. Then they want to nest it inside, then they get this tree map. Tree map, this one is I think it's one professor in University of Maryland, College Park, called Schneiderman. He actually got this file system, 5 different directories, subdirectories. You can write as a tree, but he actually wrapped this tree into this map style. This is tree map. This one actually is a real map, but you can put many items into this tree. If you surf the Google map, or sometimes even you go to a conference, or you go to a tour, for example, 2 weeks ago, I was in San Francisco. They actually have some kind of tree map if you think that way, because they give you one map is San Francisco and the surroundings, which is very big. You can look at the whole Bay Area. You can go to north of those parks or something. They get this map. But then they give you the San Francisco city map. Then they give you a small corner, say this is downtown San Francisco, downtown map. Essentially, it's a tree, right? You think about it, one part is whole northern California. Then you get into San Francisco, bigger San Francisco, then you get downtown. Everything is in different resolution. Okay? That's actually the tree map. But this tree map basically nests everything down there. Okay? Some parts, they make it very sparse. For example, this part likely is a field, so nothing interesting. Then they make the resolution very, very rough. Okay? But some other things they think is more interesting, they make it refined and refined. Okay? So then you get many different levels of resolution in those tree maps. So this is very popular use as well. You think about it currently. There are many, you go to Google, you want to drill down the Google map, you will see sometimes it's so rough, but sometimes you can see every street. So essentially it's kind of tree map, but they put it in a more useful way. Another one is InfoCube. InfoCube means you get information, you pack them in a cube way. Okay, you can turn it around, and you can see through inside what it's in. Of course, the tree map, you have to think about something is hiding behind. You have to turn it around. Okay? So that needs some nice visualization. You can get in. Actually, there are lots of software. For example, I remember early days, the Silicon Graphics. They actually have a data mining tool. Those things you almost like you wear a skater. You can actually penetrate in. You can see the surroundings. Those visualizations, only graphics people actually really can do it well. So those InfoCube. Another one is called 3D cone trace. Cone trace means you get like a tree, but they arrange the tree in the shape of a 3D cone. Okay. Then you can even say, from here I want to go to the other place. And how do you go? They draw the trails. They draw from the route, how to go step by step, finally can go to your lead. So those are the 3D cone trees. They can even map into 2D space. You can see from the top of the tree. Then you can see the rest. So those are, visualization has lots and lots of different ways you can see. You just want to represent the information in a reasonably structured way. People can either see it, and then you can map them in a different fancy way. People enjoy, reading the data. Another one I think is very popularly used in text data. I think everybody probably see this in many different ways. A lot of people call this text cloud. Some people even call it word cloud or something. This cloud essentially is representing the words in different font size in most cases, and some in different colors to give you information how important this phrase is in your whole document, what is the distribution. Give you an example. This one is I grabbed it from KDD 2013. They just look at a research paper, finally accepted, look at their title. They work out a tech cloud to represent, for this year KDD conference, what are the most important themes? You probably can see. The most important theme, pretty big, is social and information networks. But they have a graph mining, they have a recommendation systems, classification, scalable mentions or something, scalable methods, probabilistic methods. They have those different phrases, how most important, how frequent it happens in their title, they put as a tech cloud. So it's very easy to see. Even I saw sometimes in our department, when you get invited talk, for like yesterday, there was one professor from Stanford University. And in many cases, they want to show you without you do a lot of reading on the detailed abstracts. They put a tag cloud there to see what terms is most important because it happens in his abstract multiple times. They put it very big. Okay? So then you immediately know what he's doing. Right? So those are the popularly used for the documents visualization. Another is network visualization. Network is very complicated. There are social networks, information networks, but network, if you organize them in structural way, it becomes pleasing to see it. For example, if you see they form some kind of clusters, and this is the center of the cluster, these are the links across different clusters, and if you organize network in a way like this, it becomes much pleasant, much easier to see their links and the structures. But if I draw the network in that way, you probably can see it's very hard to see what's happening. Okay. Actually, this one is interesting. I got one PhD student. That time, he got actually Microsoft PhD fellow. Now he's in Microsoft Research. He got a 2015 PhD dissertation award. One piece of work, the first year he came here, he worked out turning this kind of messy network into a very structured one by working out finding advisees among like 2 million papers, right? You want to find out who is whose advisor and advisee relationship and which year. Okay. Just based on this graph, this co-author relationship in the paper. And he found a very high quality, actually, using his analytical method, finding who and who is the advisor, advisee. And he put those very sophisticated network into structures. And he showed to Army Research Lab. The Army Research Lab got very excited. He gave an example like this. He says, in the Army, suppose you got lots of telecommunications, who send email to who got a telephone conference with who, you get it so big, communication. And he wants to find who is like a general, who is a foot soldier. Okay. You just think about the communication like this, and you find it. And he actually shows, of course, he does not really have those army data, right? He actually shows in principle, you can easily get this. Why? Actually, it's very easy. You think about it, a foot soldier will regularly communicate with general. It's impossible, right? He dare not even talk to the general. So what they will do, he likely will just communicate with their squad lead. Okay. The squad lead may be communicated with the platoon lead. You just look at the communication patterns. You will be able to work out a hierarchical structure. The network is not a mess. Okay, just based on the frequency, you actually find you can work out the whole overall hierarchical structure if you have this communication. Actually, it's quite possible. Right? So he just shows that for advisee, he can work out the structures nicely. That means you need the data mining to make the network more structured. Now, we got into the visualization. If you really want to play the visualization, you probably want to take a graphics course, because we're not going to teach you how to do visualization. But the graphics people will do, right? Now we get a little analytical. We want to measure data similarity. We get lots of data, but we want to structure them some way. We want to look at whether the different objects are similar or not similar. Okay. Some people call this as a distance measure. That means whether these two objects are very far away, the distance is high. Okay. The similarity usually for numeric data, it may be easier. Sorry, I think it's just a young core. I should switch off. Similarity for numerical measure is easier to get. We are going to discuss all kinds of measures. Nominal means names, numerical data, structured data, high dimension data like documents, and many other kinds of things. But we first look at the similarity. on the numerical measures. We also look at dissimilarity. Actually, similarity and dissimilarity just reverse. You say they are very similar, their similarity is high, their distance is short, or you say their dissimilarity is low. Okay. It means these two friends are very close. That means their distance is short, their dissimilarity is high, but their similarity is high, their dissimilarity is low, right? So that's essentially similarity and dissimilarity, just different way to say. The minimum dissimilarity is 0, means they are the same, identical. And some people are using a term called proximity. Proximity is a little general. It means proximity actually covers similarity and dissimilarity. They all call proximity. Proximity is how close or how far away. Those are the proximity. It's just a mathematical term. So how do you measure it? Because each object may carry multiple attributes. So you're essentially thinking each data may have p dimensions. Okay. For example, you may have gender, age, height, or body weight, and like GPA, all these things. All these are different dimensions. Okay. If every object has p dimensions, you get n objects. Then you got this, m times p, this matrix. You get n rows and p columns. You get this matrix. Okay. This matrix we call data matrix. But in many cases, you want to look at the similarity matrix or distance matrix. We call dissimilarity matrix. How do you get this dissimilarity matrix? Is you look at you turn these objects into distances. Suppose you have n data objects. Okay. Then you check this n, each one comparing with the other n minus 1 objects. Okay. You actually also compare yourself. You compare yourself, the distance is 0 because you are identical to yourself. So that means if you say this one, the column is 1, the row is 1, 1, 1 means object 1 versus object 1. The distance is 0. Right? So this 1, 1 is 0. Similar thing, 2, 2 is 0. Object 2 versus object 2 is 0. 3, 3 is 0. All the diagonal matrix are 0. Okay? Because you are identical to yourself. Then you look at the distance between 2 and 1. Okay. The 2 is your row, 1 is your column. Then 2, 1, this distance is d to 1. Okay. That's one distance. And if you think most distance is symmetric, like object 1 and 2, the distance is same as object 2 to 1, right? So this 1, 2 to 1 should be symmetric. You only need one part. So that's why you get a triangular matrix, because it's symmetric. You write on the other one, it's the same distance. It's 1, 2 is the same distance. That's why you don't write the other part. Then you get a triangular matrix, right? So that's the way to represent dissimilarity. So you get a dissimilarity or distance matrix represented this way. Now we go inside to look at the real distance, how to calculate. That means for each attribute, each dimension, how to calculate their distance. The first thing we probably want to calculate is the nominal attributes. Nominal means names. Okay, that means, for example, you call John, the other one called David, the other one called Jean. Okay, those are all names. How do you measure distance? Okay, that's pretty hard, right? Actually, if the name has no real value, can be mapped. For example, you get the name John, David, Jean. You cannot map to 1, 2, 3. How do you calculate their distance? Very simple. You will say, if they are identical, these two both are Jean. Okay, they are identical, their distance is 0. Otherwise, their distance is 1. That means they are different. So that's simple. Then if you got two objects, I and J, how do you check their distance? If they are all names, for example, this could be a street, this could be a city, this could be a state, this could be a country. Okay, they are all names. Okay, you have n dimensions. Then how do you check their distance? The first thing is, if you have total p variables, everyone is nominal, is named. Okay. The distance, the simple distance is you take total p. If you have m matches, for example, you get the same last name, same first name, you get the same, birth, country or something. You say, oh, our distance actually is very close because we have the same last name, same name, same first name, same country. So you do just name-wise, you can say the same. So that distance is based on the string distance, right? Either you are identical, distance is 0, or you are different, the distance is 1. So that's a way you can do the simple matching. Another one is you can map them into binary variables. Okay, of course, name is hard to map, but if I give you something like a color, okay, you can map them as red is one dimension, yellow is another dimension, blue is dimension. So you will say, if it's a red is red, then that's a binary. Then you get identical 0, 1. It's the same thing, but you will have a long vector of all the different things. Okay. So that's the mapping of the new nominal data. Of course, most people do not compute nominal data in this way. Later, we are going to discuss the other semantics. Here, you do not consider semantics. You map it, just yes or no, it's identical or not identical. That's it. Okay. Then, even that, it still will be useful. Why it will be useful? You think about this. Suppose you go to see a doctor. Okay. The doctor may say whether this person, this part is normal, this part is abnormal. They may say heart, lung, or temperature, or something. Then they actually can give you something like high and low. Okay. Is both high? Okay, then they say they are the same. Okay. Or you test this one both positive and negative, that's the same. Okay. But in many cases, they do not write down as name. In medical discussion, likely they want to have a binary variable. That means when you do this test, they will say this positive or negative. Then you get only two states. Or you say whether you have a fever, they will say yes or no. Yes is you have fever, no, you have no fever. So that case, actually in many cases, they don't want to write down a string because string is hard to interpret. They write as binary variables, yes or no. Okay. Then this binary variable becomes very useful. You think about it, you get a patient, the nurse will check, the doctor and nurse will communicate each other. They communicate in this, whether this patient has fever, whether this test is positive, this test is negative. They give you a binary variable, you can easily say how many things are wrong or how many things are right. So those are the binary variables. Binary variable to calculate their distance, whether these two patients are similar or not similar. Actually, there are two kinds of binary variables. One they call symmetric binary variable. Another they call asymmetric binary variable. What is symmetric? Symmetric means you assume the distribution on this value, 1 or 0, this binary variable, their distribution is somehow even. Normally, it's sort of evenly distributed. Just give you a simple example. Suppose you get a gender. Okay, the doctor get into the patient is either male or female. The chance in most cases is the same. Okay. Then they will say this binary is symmetric. Symmetric means the chance to get a male or chance to get a female is almost identical. Okay. So they do not think anything right or wrong. So then this is symmetric. What is asymmetric? Asymmetric, for example, you got fever, the other guy got no fever. If the majority of people you tested is no fever, the fever means alarm. Okay. Like some people tested like HIV positive. That's alarm. Okay. You get anything you tested in the medical, usually 1 means something is alarm, 0 means it's not. So this is not symmetric because the doctor look at it once, they pay much attention than zeros. Right? Because it's normal, you put a 0. 1 means something abnormal. Those things means asymmetric error. Then when you calculate distances, you probably want to treat them differently. So we give you a table. You probably can see how do you calculate distance if you treat it, symmetric or asymmetric. Okay. For example, you get 2 objects. You can think these are the 2 patients. Okay. Then you get lots of medical tests. So how many medical tests you got? If you look at this, you probably can see you get a Q, R, S, T. They all add together. That's the test you finally got. Okay. But if both are 1s, okay, that you get a Q times. That means you test the Q different things. These 2 patients, I and J, they both show positive. Okay, a Q times. Then this one says object I is positive, object J is negative, or is 0. You get R times. Okay. This one is this object I is 0, object J is 1, you get S times. And both are zeros, you get T times. So that's we call contingency table. Or you in many cases, if you play with Microsoft like Office, Excel, you got this kind of table quite a lot. Right? So, but the difference is here, these 2 are 2 objects, and these 1 and 0s are the dimensions or variables. You got the real value. Okay. This just how many times are identical, how many times are different. Then you can see the formulas are different for symmetric, binary, and asymmetric. Right? Symmetric binary, the distance, you probably can see how you calculate that. Okay. How many times are different is the distance. You got 1, I got 0, we are different. Okay. Or I got 0, you got 1, we are also different. Right. How many times they are different? You can see you get a R times. Object I got a 1, but object J got 0. You get S times is the other reverse. So total number of differences is R plus S. That's the numerator, right? That's the one you say we are so many times different. You divide by total times you measure. Okay. That means if we measure, 20 different variables, we got a total 5 things are different. So it's 5 divided by 20. So that's the symmetric. But in real life, you really go to hospital, they pay much more attention on 1s than 0s. They assume 0 is, you do so many tests, if it's normal, they put you as 0. The doctor just ignore that part because they think everybody should be normal. Okay. So in that sense, what they do is they ignore the double zeros. You got 0, I got 0. The 0 can be tossed away because there's nothing important. Then they pay attention on both 1s or any 1 got a 1. Right? That means anything you turn out to be positive, the doctor pays attention. That's why you get the measure is somewhat different. What's the difference? You drop T. What's the T? T is double 0. That means when you look at 2 patients, those things like no fever, they both no fever, no cough, they both no cough. They actually ignore those parts because they want to look at these 2 patients, how different they are. You may test 100 different variables, but all should be 0. You are all 0. They just toss it away. Right? They look at difference as they look at anything got a 1. Right? So that's the one they call for asymmetric binary variable. This is the way you measure it. And this is the way actually has a very, very good name. They sort of call the Jaggard coefficient. Jaggard coefficient just because Jaggard is the early mathematician pays attention on this. He actually gives this measure. But he wrote it different. Because here we put it as D means E similarity or distance. He put it as S means similarity. So that's why these two formulas, you see there's a difference. Excuse me. The difference actually is you put R and S, how many times we are different. He put as Q, how many times we are the same. Okay, so it's, if you look at this two, you just say this one just 1 minus this one, you get this, right? So this is D similarity and similarity, just like a 1 minus that you get. So it's very easy to convert. So rigorously say this one is a Jacob coefficient. This one, some people actually loosely call this one Jacob coefficient. But essentially it's just a distance for asymmetric variable. Actually, it's interesting because this one developed a long time ago, Jacob coefficient. Then in data mining around the year 1990s and 2000, some people try to define the association rule, those measures. They found one measure called coherence measure. Then they use those support or something to get a pretty complicated formula. But they did not realize this formula, if you get a Q and S, you minus this, you got exactly the same as Jacob coefficient. They just write it a little different. They found a new measure. They claim something so exciting. And finally, people watch it. They say, what you found is just people found it 50 years ago. Okay, that's the Jacob coefficient most popular. You probably can see. Rediscover the wheels actually could be quite common, right? So because the wheel looks different. Okay. So that's just a typical measure. Then we look at the real computation. Okay. Suppose we got 3 patients. Their gender, their fever, cough, test 1, test 2, test 3, test 4. You get all the different things. But you know gender is symmetric attribute. Means gender, the chance to get a male or female is almost identical unless you test some disease just for one gender. Okay. Otherwise, you test the general patient, you want to find these 2 patients whether they got the same problem or different problems. They actually ignore the symmetric variable. They only calculate this asymmetric variable. For example, whether you got a cough, whether you got a fever, whether your test on this one is positive or negative, right? So now I would like to ask you whether Jack and Mary got some likely similar disease, or Mary and Jim got likely similar disease, or Jack and Jim got similar disease. How do you calculate? So you can see the similar disease means their difference, this distance, is the smallest of all, likely something different, right? So you can see what you do is you just map those things into 1 and 0. Obviously, you want to map those important things like yes things or positive things into 1. Those unimportant things like negative things into 0. So once you map this, you can use those asymmetric variables to calculate their distance. Of course, you can map it to calculate it. I just calculate it for you if you can see that. Then you can calculate the distance. You can easily see Jack and Mary likely got the same problem because their distance is the smallest one. And the other one, the distance is far bigger. But they may have different problems. So that's the way to check the similarity in medical tests. It's very popular. Asymmetry. So that's just an example you can see. Now we get into numerical data. Numerical data means the data actually measured in numbers. In most cases, real numbers. Right? You allow them to have decimals. To measure the numerical number, some very big, some very small, in many cases, if you want to find the nice ones, you actually, to look at their distribution, you want to measure them relative to distribution. So Relative distribution, you use z-score. I do not know how many people know z-score. How many people know z-score? You can raise your hand. Yeah, it's to my surprise, it's only half. I think it should be more, right? So essentially, this z-score, if you know a little statistics, is you look at this x value deviate from your mean, deviate from your center value. Okay? Whether it's positive or negative, of course, if this mu is higher, you minus this one, you get negative one. It means you are lower than the average, right, the center. Then you divide by standard deviation. That's your spread. Okay, you divide this, you see how many standard deviation away. Right? So it usually should be below 1. That means the majority of data should be within 1 standard deviation. But if you minus this, you get a 3 standard deviation away. Likely this one is like outlier. Right? We know that. So that's a z-score. You measure it. If it's very big, negative or positive, usually those are outliers. Otherwise, majority of data will be within 3 standard deviation away. That means plus or minus 3. Usually it's within this. In most cases, really plus or minus 1. Right? So that z-score is easy to calculate. You can easily measure whether is normal or abnormal. Right? Some actually measure this is doing. They think this one goes too quick. They actually doing this one called mean absolute deviation. That means you use your measure, you minus this one, you take the absolute one. That means you think plus and minus will not cancel each other, right? Then you take the absolute value, you can get another kind of mean. So that's different. They call this one the standardized measure. But whatever, that's the most popularly used. Now we look at the real data, how we look at their distance. The distance, actually there, I think most people knows Euclidean distance. I will not even for a vote. If you do not know Euclidean distance, you probably should not take this course. Right? But actually the distance, the most popular used, this general form of distance is Minkowski distance. Minkowski distance means if you want to see I and j, how far apart these two numerical vectors. Okay? Two numerical vectors, the simplest one, of course, you can think of 2 points on the map. But in many cases, it could be multiple ones. Suppose you get p dimensions, p variables. You look at everyone's real value. You take the absolute of their distance. Then this h will change. Okay. This h, if h is 2, it is actually the Euclidean distance. But if it's 1, it becomes Manhattan distance. Okay. And what about this one is really big, like infinity? They actually have another definition for it. Okay. But this Minkowski distance has a very nice property. They have this they call magic property. Magic means the distance in any case is greater or equal to 1. When they are identical, it's 0. Okay? Otherwise, it's greater than equal to 0. Okay? And they are symmetric means the distance between these two objects, no matter is it I to j, j to I, actually they are identical. Okay? This is symmetric. Another one is triangular inequality. It means that you go via another point. It will be usually belong. So I think you all know this. But now you look at the h, you take different values, what will happen. Okay. If h is 1, essentially the distance becomes Manhattan distance. Manhattan distance, some people call this one is L1 norm, or call this one city block distance. It's just based on this formula. It means each one, okay, if you think about it, you go in Manhattan, okay, you cannot cross in the center of the big block because they fill up with all the buildings. Okay. How you do? You have to go to the city block, go to the intersection, you turn it around. So even you look, it's not too far away. You have to follow the grade of the structure. That's the city distance, the city block distance, or Manhattan distance to follow this structure. Each one you think is like a one-dimension grid. You go to the other dimension. Euclidean distance is you measure the real, using the typical measure, you pick the shortest, one. That's the 2D dimension, right? But in P dimensions, you're still using this. You get a square, then you take the square root, you get infinity. Of course, H can be 3 and 4, but actually the most popular used H value is 1, 2, and infinity. What do you mean infinity? Okay, you can think this way. What is infinity is this H keeps growing. Okay, 2, 3, 4, 5, you keep growing to really, really big. Okay, into infinitely big, you got this. Then you may say, wow, this will be really, really hard to compute because 2 already takes some effort, 3 take more effort, 4 take more effort. Because infinity, I will take infinite effort. Is that true? Actually, it's not true. The infinity actually becomes very, very easy to compute. It's almost take no effort, you can get this infinity computed. How do you do that? Okay. If you just look at the formula write down like this. Okay. You get a P dimension. You get H. This H can go from the very low up to infinity, but every time you take these H, you take the root. Okay, it's also. But this one, actually, once you calculate this, you can easily find. This one is whichever your dimension is the maximum one, you just take it. Then you get it. What do you mean? You think about this, okay? If you just think it, suppose you take you first is thinking about Manhattan distance. You say, here I go 1 block, here I go 2 blocks. Okay. This is 1 and 2, that's the distance. Of course, you take 1 and 2, you calculate, let me see. We just take this 2. This is the x3, this is the x1, x3. Okay. That's a very easy. You take a Manhattan distance is 3. You can see this is 3. Right? Because you go 1 block here, you 1 block up. Okay. Euclidean distance, you calculate this. This is the square root of 5, right? Those are very easy to calculate. But what about this infinity we call supreme distance? And you just think about how do you calculate. This one, this 2, you get a power higher and higher. Okay. This one, higher and higher. And what about they go to infinity, you take that square root, what do you get? You get 2. Why you get 2, not 1? Not other values. Because 2, when you power up higher and higher, this 2 becomes dominant. The 1 has nothing to say. Right? You think about this. Once this 2 going higher and higher is dominating, once you go to infinity, that's only me. Right? It's only 2. So it's very easy. You can just imagine. Becomes extremely easy to compute on this supreme. Right? So now probably I can show you, I think Manhattan Euclidean, you don't need to lecture on it. But you look at the supreme, okay? x1, they are identical because to itself, no matter what, right? Then x1, x2, actually x1, x2, these both are 3. Then no matter your square root or them or do whatever is 3, you get infinity is also 3. Right? But if you look at the 1 to 3, 1 to 3, you get the value is 2. Why is 2? It's also, you can easily imagine. Of course, you can calculate it. Easily imagine because this longer one will dominate. Once you get more and more power, this one will have all the states, right, and the other. That's the reason. It's very easy. I may ask you to compute. Okay. It's so easy. You don't have to keep the power. You take the bigger one. That's it. Okay. So that's about a numerical value to compute different kind of distance. Then we look at the ordinal value. What is ordinal value? Ordinal value means there's a rank there's a, for example, okay, suppose you were a freshman, here's a senior. Okay. Actually, you know there's an order on the different numbers. You get a freshman, you get a sophomore, you got junior, you got senior. Actually, you will say, oh, you will need another 3 years, you also get into senior. So you actually know the distance because they are ordered. You know the distance. The same thing as you probably go down to military. They have all the things into general. They have so many layers, right? So you actually get into from the squad to the soldier, sergeant, you go down to the general. All the rank are ordered. So we got an ordered value. Then how do you calculate this order value? It's also become quite easy because you can map this one into a value, right? For example, you can say freshman map into 1, then senior map into 4, right? Then freshman and senior, their distance, actually you can calculate this one. So if you map something between this, you can calculate their distance. Right? So that's ordinary. Okay. What about if you have all kinds of variables in your object? You think about the object is person. The person may have a name, which is nominal. You may have an age, which is numerical. Then you have something which you can count as binary or something. You get all kinds of things. But what about I want to calculate the distance between these two people? Then if you want to calculate these objects, you have to think about all the dimensions, but they have different weights. You can think about different weights. It's more like you think about our course. You have homeworks, you have programming assignments, you have midterm, you have final, you have projects. All these have different weights. Finally, you add them together in a weighted way, you got the distance. So that's the same thing. The distance is you add them together. This delta means you give different weighted factor. So finally, you add all these weights. Usually should be 1 or 1, whatever. So you can divide them. Right? So that's a typical way to calculate the distance. But what about high dimension data? Okay. What is high dimension data? Actually, you are going to see a lot of high dimension data. I'm going to show you a most popularly encountered one document. People want to measure the distance between documents. That means whether these two documents are talking the same thing or very different things. How they want to measure, how they can measure this. Most document model, they call this is a bag of words. That means you are thinking the document in the simplest way is document contain lots of words inside. But why I call this one the bag of words, it's not set of words. Because you repeat these things many, many times, it's important. Okay. For example, when you're talking, suppose you report Olympics. For Olympics, now you report about swimming. Okay. You talk about swimming for this whole article. You get a swimmer or lots of different swimmers or different scores many, many times in this one. And you say it many times, it counts. It means you say swimmer or swim or medal or gold or something, say many times, this one will add it up. That's a bag because you mention swimmer 3 times, the swimmer will count as 3. Okay. So that's the case you can see here in the document. They want to see whether these two documents are similar or not. You take every word like a team, coach, hockey, baseball, soccer, penalty, all these things. Every word will count. How many words you have? You have a lot. Right? Of course, most time you will drop those stop words, like off and on or something, drop them. You only take the meaningful words, but that's still a lot. You get thousands of them. That's why you have very high dimension, because every word you count as a dimension, you get thousands of dimensions. Okay. And for those thousands of dimensions, if you found this word, like a coach, not even appear in this document 1, then you say 0. What about this team occur 5 times? 5. That's why you got this one is a bag But you get a very long vector, right? This vector, another thing I probably should say is, in principle, the words are not ordered. But if you want to compare them, you have to order some way you can compare them. That's why finally you get a word vector. It's not a set, strict set. You get a vector. Okay. But the vector, whether put a coach in front of team or not, is completely your choice. So to that extent, the order doesn't matter. But you compare them, you want to line them up. Right? But how do you compare these two? That's very hard to compare. You remember we said, you get a 1 and 0. You get so many 1 and 0s, and you get so many numbers. How do you compare them? Compare two vectors. The best way to compare is the cosine distance. Okay, they call using cosine measure. If you think of cosine like this, you get two vectors. Okay. You want to see how these two vectors far apart? You take their cosine. Right? That's exactly the cosine measure comes from. Right? So how do you do this? You can think everything is a long vector. Then you want to compute the distance between these two vectors, how similar these two documents, or how dissimilar these two documents. You take the vector d1 and d2. Every one is a vector. Then each vector, you look at their own, like the measure, the length. And then you take the dot product of these two. Remember, you could compute two vectors. You need to take the dot product. How to do dot product? Like 5 times 3, 0 times 0, 3 times 2. Then you add them together. That's dot product. Very easy, right? So how do you calculate length? Length essentially is 5 times 5. Then you get something that's the 1, right? You can easily calculate the length, so you take the square root of the same. So you probably can see, how do you calculate I just take these two vectors. You can see how to calculate. This dot product is you just time up each one, right? You get this. You add them up. Then you calculate the length of d1. How do you calculate this? You time itself. Right? Then you get 5 times 5, 0 times 0, and then you take square root. So that you get a d1. Same thing. Then you finally try to calculate the cosine. You just take this dot product divided by the product of these two vectors. So you you probably can see this 0.94 means actually these two are rather close, right? Because it's closer to 1. Right? You can see because they mention team, they mention some words many times, they mention similar number of times. If they do not mention anything, they get similar number of 0. That's why these two documents are rather similar. That's a way to calculate cosine for high dimension. Actually, this high dimension is not confined to documents. There are many high dimension data. For example, if you test like a microarray, there are 10,000 dimensions you may want to compute. There are many high dimension data. This cosine similarity, to some extent, is very popular for high dimension. Then, before we finish this chapter, I want to introduce another important one. But this one is a little trickier. This one called KL divergence. You want to compare. Now you're not comparing two vectors, but you compare two probability distributions. Just wondering, how many people heard KL divergence? Okay, we still have quite a good number. I think about 15 to 20% of people know this KL divergence, which is very useful. Okay, that's why I want to introduce it here. But this one, I first should say, this one is not a typical distance measure. That's why we call it divergence. We do not say distance. Most of the distance measure is metric, it's symmetric. Symmetric means, okay, symmetric means A to B, B to A, they have exactly the same measure. Okay. The distance between A and B, you can either say A to B or B to A, they're the same. But a KR divergence, you calculate, you put in the front or you put it, one the other, they are different. Okay? They are not exactly the same. That's why we do not call this one as distance. We call this one as divergence. Okay? But we just ran out of time. The next lecture, I'm going to give you the detailed calculation on this KR divergence. Okay, thank you.